Alright, here we go, Chapter 3, Section 2. We're going to use applications of radians, so we should be able to calculate the arc length or the area sector of a circle, given either the radius and something in degrees or a measurement in radians when we do this. Okay, so make sure you write this equation down. The letter S represents the arc length. Okay, so what is the arc length? It's kind of it's a chunk of the circumference of the circle, all right, that's based on the given angle, so how far that's opened up. So if we look at the S, it's drawn in purple here, right? S is the arc length from point T to point R on the circle here, based on whatever angle that is. So that's really how we have to understand what arc length is. It's a portion of the circumference of the circle. So you need to write down S equals R times theta. Theta is the angle in question. R is the radius of the circle. Theta must be in radians. Notice that's in bold here. Theta has to be in radians when you do this calculation, okay? So let's still go through an example. Make sure you write this down and draw it out so that you have it in your notes. Okay, a circle that has a radius of 18.2 centimeters. We want to find the length of the arc intercept by a central angle that has a measure of 3 pi over 8 radians. Okay, so for us, theta is going to be 3 pi over 8. R is 18.2. We literally just plug into the equation. S equals R theta. So when we substitute in those values of 18.2 for R, we're going to multiply by 3 pi over 8. What I would do for you in your calculator to make sure you do this problem and get the exact answer that I'm about to show you. But take 3 times pi, hit enter, divided by 8, hit enter, then multiply by 18.2. Make sure you're kind of doing it in that order so that you get the correct calculation when you go through this. You should get approximately 21.44 centimeters. Okay, so it's a length, so we should have centimeters as a distance as well. So that's a chunk of the circumference, okay? S is the arc length, all right, that we calculate based on that given angle for a chunk of the circumference of the circle. Let's do another one now. We have a circle that has a radius of 18.2, so it's the same circle, right? But we want to find the length of the arc intercept by a central angle with a measure of 144 degrees. All right, so if we remember from earlier that theta has to be in radians, our first step is to convert the 144 degrees to radians. Anything that we are doing in arc length for this section has to be in radians. So remember, to convert theta to radians here, we have to multiply by pi over 180. So you're going to take pi divided by 180, multiply it by 144, and you'll get 4 pi divided by 5 radians. All right, you can use the decimal version of this as well, right? It's approximately 4 times 3 is 12, so it's a little bit more than 12 divided by 5 there, okay? So S equals R theta. We have R, we now have theta in radians, and we substitute that in and plug it into our calculator. We get 45.74 centimeters, okay? So same circle as before, just using a different angle. This time the angle was given to us in degrees. The first step we had to do was convert degrees to radians, and then we had to substitute our radius and our theta that's now in radians into the S equals R theta equation. All right, now let's talk about how we can find the distance between cities in the United States or things like that. But what I want you to remember from geography or things like that, we had longitude and latitude. All right, remember lat is fat. Those are the angles that go around the outside of the earth, and we start at 0, right, which is the equator, and we have the northern hemisphere and the southern hemisphere. So this is where we get the actual measurements for latitude and longitude, but we're going to just apply latitude in this case. So everything for like our GPS and mapping systems is laid out like this. Our latitude lines and our longitude lines are all in terms of degrees. Okay, so the United States alone, most of the United States, the 48 states, lie between 30 and 45 degrees latitude, okay, north, because we are north of the equator. All right, so Alaska, a little bit higher up, all right, it's between about 60 and 70 degrees latitude, all right. Hawaii falls between 15 and 30 somewhere, probably closer to about 20 degrees Hawaii. So remember the equator, all right, the equator goes through South America, all right, so it's not technically like, you know, where Mexico and South America come together, but the equator kind of goes above the Galapagos Islands, all right, and goes through Ecuador, where you can actually stand on it and things like that. So just a quick geography lesson. So zero's in the middle, right, and then we go up by, you know, 15 degrees puts us through Guatemala, and then 30 degrees puts us, you know, kind of through, I want to say Dallas, Texas sort of thing. 45 degrees puts us up north towards where Portland, Oregon is and things like that. So just kind of a frame of reference as we go through this. And I'm cheating, I'm looking at a map, so don't think that I know any of that off my head. But I have a big map in my office at home that has all the latitude, longitude degrees, because we marked everywhere in the world we've been with little pins, so I can cheat and look at that. But that's beside the point. Let's take a look at this problem here. All right, so the important part is the latitude of Reno is 40 degrees north, and the latitude of Los Angeles is latitude of Reno is 40 degrees north, and the latitude of Los Angeles is 34 degrees north. So there's 6 degrees of separation between the two cities. All right, the radius of the Earth is known to be about 6,400 kilometers. We want to find the north and south distance between the two cities, because remember the Earth is a sphere, unless I guess you're a flat earther, but the Earth is a sphere. So technically there's an arc length that goes between Reno and LA. All right, so if we take a look at the picture here, and it helps to draw these out. So we start from the equator down at 0, and we go up to 40 degrees, and we can draw Reno. And then we start at the equator, which is 0 still, right? And we draw up 34 degrees and see Los Angeles. So we can see the difference between Reno and Los Angeles is 6 degrees. Now we have to remember that we got to take that 6 degrees, that theta, and turn it into radians. So we're going to take 6 degrees and multiply it by pi over 180. So when you do that, we roughly get pi over 30 radians. Okay, that's our theta. All right, the R is of the Earth, right? So we have 6,400. We're just substituting into S equals R theta for the circumference, or the right. We're not using the circumference of the Earth, but we're finding the arc length. All right, just that chunk of arc length that's for the 6% of theta. Okay, so S equals R theta. We're going to take 6,400 times pi divided by 30, and approximately we're going to get 670 kilometers. Make sure when you're doing this or watching this that you pause the video, get your calculator out, and make sure that you are plugging these values into your calculator and you are getting the same results. If you're not, or if you're struggling, let me know so that we can make sure that you're getting these calculations down, because it's very imperative that you're not struggling with the calculator through this. Okay, so roughly the distance between Reno and Los Angeles, based on arc length, is 670 kilometers. All right, let's take another one. We got a rope that's being wound around a drum with a radius. All right, so an old catapult or something like that, where we want to crank something up. Okay, we've got a pulley system. We're pulling it in, winding it in through. Okay, so the drum has a radius of 0.8725 feet. Okay, how much rope are we going to need to wind it about 39 degrees or 39.72 degrees around the drum? Well, what's your first instinct here? I have a radius, all right, and I have a theta, but that theta is in degrees. So your first instinct is I got to take 39.72, multiply it by pi over 180 to make sure that I get my theta. All right, and then I multiply that by r. This one's just kind of showing the complete, step all in one here. So we have the 39.72 degrees times pi over 180, and then the r is 0.8725. So we're multiplying those out. So the approximate amount of rope that we're going to use is 0.6049. Okay. Hopefully these problems or these examples are fairly easy, right? We're just finding r, finding theta, substituting it in. All right, this one kind of takes you to the next level a little bit, because we got two different things impacting each other. So if we're looking at example 4, we have two different gears that are working together here. All right, so I'm going to tell you that the smaller gear moves a lot faster than the larger gear. Those of you guys that were in mechatronics, that should be solidified in you from the mechanical class, all right? But all right, so let's take a look at this. If the smaller gear rotates through an angle of 225 degrees, through how many degrees will the larger gear rotate through? All right, so we got to calculate a few things here. We got to calculate the distance, all right, that the little one travels, because it will still be the same distance as the big one travels. The angle on the big one, though, will be much smaller. All right, so the big one's going to take a lot more for one complete circle, but they will still both travel the same distance where they're actually touching each other. So you need to think about that as we go through the problem. Okay, so we have the smaller gear, we have its radius, and we have its angle. So we need to find how the total distance traveled by the small gear, because the large gear is going to travel the same distance, it just won't take as big of an angle. All right. First step, you see that it's 225. You should know, all right, I got to take that theta and I got to put it into radians. Okay. So that's the most important part when you do that. So 225 times pi over 180 ends up giving us 5 pi over 4 radians. All right, we're given the 2.5 centimeters, so we just substitute in r and theta, and we know that s, the arc length of the small gear, is approximately 25 pi over 8, right? If we take 2.5 times 5, that's where the 12.5 comes in from. All right, just hasn't been converted to a decimal here. Now, that's the total distance traveled by the small gear and the total distance traveled by the large gear. But what's the point of the problem? I'll back up right here. The point of the problem is, how many degrees is the large gear going to rotate through? All right, so that's what we're trying to find. Now we're finding theta of the large gear, and we're given, or we just found its S, and we know what R is. R is 4.8 for the large gear. All right, so we got to do a little bit of algebra here. We're actually solving for theta now. When all the other previous examples we've had, theta's been given. But in this case, we're going to solve for theta. So S equals R theta, or theta is equal to S over R. So we're going to take this arc length that we just found and divide it by the radius of the gear, and that's going to give us what theta is. All right, simple algebra manipulation. So theta is going to be 125 pi over 192. Now you're asking, hey, why is this in, a fractional form and still have pi and we're not using the decimal? Because theta is in radians here, and the question asks for angle. So we still got to take this answer and multiply it by what? 180 over pi. All right. So when we multiply this by 180 divided by pi, all right, the pi's cancel out, and we do the math, we approximately get 117 degrees. Okay? So, in essence, the small gear has to move 225 degrees. For the large gear to move the same amount, it only has to move 117 degrees. Okay? Very, very important stuff there. But cool, so this is a different one where we're solving for, a different variable based on a given scenario. All right, next part. This might be like those of you guys retaking the ACT. This might be good for you to know, because I've seen where there's been an area sector or an arc length problem on. So now you know how to do an arc length, S equals R theta, and this will help you do an area sector of a circle. So you should be good to go. There's might be one or two problems on the ACT that you're like, oh, now I know this stuff now. It's usually maybe one or two problems like towards the end or things like this. So what we're looking for is the area sector of a circle. So when you're looking at this drawing here, it's the shaded region now. So not the arc length, but it's the shaded region here. So I like to say, hey, think of it as a chunk of pie, right? I love pie way more than cake. You can think of it as cake if you want, right? But if you cut pie up into different area sectors, all right, this is what it would look like. So we need to find the amount of area of a sector or a section of a circle. Remember, the area of a circle is pi r squared, right? But we want to find only a section of that based on our theta. So this is where this comes into play. So the equation for us is area is 1/2 r squared theta. What changed? All right, every circle is normally pi r squared theta, because why we use that? Because we find half of that. But in this case, we're going to use 1/2 r squared theta, and we still have to make sure that theta is in radians. The ACT will probably give it to you in degrees, just to convert that degrees to radians. So make sure that you're using radians. All right, so realistic application here. A sprinkler system, okay, or an irrigation system. We want to know how much area that's going to cover on your sod at your house, or if you're doing a field of corn or some other crop, okay? So we have a center pivot irrigation system. It provides water to a section-shaped field with the measures shown below. Find the area of the field. So what are we given here? We're given an angle, theta, which is 15 degrees, and we have a radius of 321 meters. The first thing you should be thinking in my head, all right, I got degrees, I got to go to radians. So I got to take that 15 degrees and multiply it by pi over 180, and that's going to give me the radians that I'm looking for. So when I do that, I'm getting pi over 12 radians. All right, some simplification. 15 goes into 180 12 times. So that's why we're keeping it as pi over 12 right now. Now we plug in. Okay, we're going to use the formula. We know what R is. Area is 1/2 r squared theta. So we substitute in R, and we substitute in the theta, which is pi over 12. So it's going to be 1/2 times 321 squared times pi divided by 12. All right, and when you plug that into your calculator, we can approximately irrigate with this one sprinkler head, 13,500 square meters. So this wraps it up for this section. The two things we found is arc length, S equals r theta, and we've found the area sector of a circle, 1/2 r squared theta. The only really differences that you might see on your homework, all right, is S equals r theta. You might have to solve for S, you might have to solve for r, or you might have to solve for theta. That's what you would do with finding, the arc length in the first part of this lecture that we went over. In this, all right, if we look at this one, this is area sector. You might solve for A, you might solve for R, or you might solve for theta. That's really going to just be the differences in the homework problems there. Nothing super tricky. I'd say the most challenging one was the gear one, because we had to use one to impact the other. So once again, you got questions or anything, email me or contact me. Else, the rest of you guys, we'll see you in class.